and action? All right. With addition polymers, this is the same as an addition reaction. If you remember an addition reaction, you have an unsaturated compound, which means that there's two carbons with a double bond. Or it could be a triple bond too. But with polymers, it's always going to be double bond. This part is new, the radical initiator. What is that? I'm going to show you what that is, but just keep in mind that this is the same as the addition reaction. We'll start with, now this is going to be the simplest we'll do first. The simplest unsaturated compound, you have to have at least two carbons to have something unsaturated. So it would be ethene. Most of the world calls this ethylene, even though that doesn't fit with our system of naming. That's what people generally call this molecule, is ethylene. I'm going to give you a moment to go ahead and write that out, and then I'll talk about this and describe what's happening. No, I'm using R, but it doesn't represent a carbon chain this time. I'll tell you what that is in a second. So here's what's going on. You know that in a double bond, there's one sigma and one pi bond. The pi means that the electrons are above and below, not in between. Those electrons that are being shared in a pi bond are vulnerable. They're kind of out there, and they're not really protected. The sigma bond, right in between the carbon, the two carbons, the carbon and the hydrogen, those are kind of protected. And it draws those atom close together. So it's hard to kind of get at them. But the pi bond is not hard to get at because they're not in the same plane as the rest of the molecule. So what we do to start this reaction is we'll take a substance that can make an unpaired electron. An unpaired electron has a different name. It's called a radical. That's what I'm talking about here. A radical is an unpaired electron. We're going to make a polymer with a radical in the lab on Monday. The radical that we're going to use, or the compound we're going to use, is benzoyl peroxide. Peroxides are very good for making radicals because the peroxide bond is not a strong bond. It's an unstable bond and it breaks. And so when the peroxide bond breaks, then you have two oxygens each having an unpaired electron. And that's what we have here. That unpaired electron wants to bond with something else. A single electron spinning in an orbital, it's not the way the orbital is the most stable. Orbital is stable when it has an electron spinning like this and another one pairing up with it spinning the opposite way. So that thing is looking for something to react with, and it finds the pi bond. It's going to cause that pi bond to break by grabbing onto one of the electrons that's being shared, and we're going to assume it's the one on the left. It could be the one on the right, but we're just going to all use this as our convention. It's going to bond to the one on the left. So the radical is now paired up with one of these bonds. That pi bond was one electron from that carbon and one electron from that carbon. Now the carbon on the left is now no double bonds, but it's now got all 8 electrons around it. This carbon, it had its pi bond break, so now it has an unpaired electron. Right there. That was not a mistake. I meant to put an unpaired electron on that carbon on the right because this thing now is going to be very unstable and look for something to bond with. So another ethylene molecule, an ethene molecule, is around. That unpaired electron will attack that pi bond. And that's the way an addition polymer is going to work, is that it all starts with something introduced into the monomer that has an unpaired electron. It attacks the pi bond breaks. The single bond is done, the sigma bond is there. It makes a single bond now. The R, this radical, this initiator, is on the molecule, but those unpaired electrons they will grab other pi bonds, and this thing perpetuates out, and it grows really fast because that thing is super unstable. Anything that it can grab onto and react with, it does. And the pi bond is the most vulnerable thing, so it just keeps going. Until those molecules run out, this thing just keeps growing. So, this radical attacks that pi bond, and we wind up getting a string of 4 carbons. Now the 4th carbon has a radical. It will look for another. As soon as it takes the next pi bond, there's 2 more added on, and then 2 more, and then 2 more, and it just keeps going. Yes?
So like there's only one like radical initiator is needed. So what if like we have a solution of ethylene and we just add 1 molecule of radical initiator? Would it work?
Yes, it would work. It would polymerize the entire thing into 1 chain. Yep. And it would be a very twisted, distorted, like if we couldn't follow the chain, it would be too wrapped around itself. As the chain just grows, it'll kind of react in a big, messy, chaotic way. Yep. There was something I was going to follow that up with. Oh, thank you for asking that, because one thing you want to be careful of is when you add your initiator, this R thing, you don't want to add too much of it. What happens if I add too much of the initiator? What's going to happen to my chains?
It's going to stop.
Yeah, it'll start. You'll start polymerizing, but if there's too many of these things, when it starts to grow, that unpaired electron, if there's any radical around from this initiator that you added, it'll stop the chain from growing, and chains never get very long. You know how I had mentioned just about the time I was spilling that dichromate all over myself yesterday, I was picking the plastic jug up. It said high density polyethylene, HDPE. You can also make low density polyethylene, and that's got different properties. I think that's more flexible. That would be used for, not used for, in order to make it, I just got sidetracked. In order to make it, you'd add more of the initiator to it, and therefore the chains would be shorter, and you'd get different properties of your polyethylene. So this is the way polyethylene would be made. We start with ethylene, and it just grows like that. Notice we start with double bonds, and we have all single bonds in the parent at the end. Yeah?
So an example of the R is the one like that could be like halogens.
Yes. Yes, it could be. Now the initiator that we use in the lab is going to be this molecule. As soon as you see that in the molecule, it's unstable, because oxygen does not share well with other oxygens. They both are very selfish. They want to try to just yank the electrons away. This is benzoyl peroxide. And so that bond right there between the oxygens breaks, and that's where we get our radical in the lab. Now, I'm not telling you what's polymerizing. This is just used to start the reaction. This is really not the star of the show. I mean, we pay attention to it like, oh, this thing has to start with the R, and it does. But the plastic, the polymer that's made at the end is far more significant than just this silly little thing that started it, okay? Because remember, these chains can grow 100,000, 1,000,000, sometimes more carbons long. The one little thing that's there on the end of it doesn't have any significance. And a lot of people ask that, well, you know, what does that do to the polymer? It does nothing. When you have, if I had $1 million and you came up and gave me $1, I wouldn't be that excited, because I already got 1 million. And that's kind of the same thing here, is if we have 1 million carbons and there's just one R that's not a carbon there on the end of the chain, it doesn't really matter. It's insignificant. I have the next slide has a different monomer on it. This is the formation of polypropylene. Polypropylene is the plastic that is used to make sour cream tubs and butter containers, things like that. It's an opaque plastic. So polypropylene begins with propylene, which we know as propene. It's got a double bond there between carbons number 1 and 2. And then carbon number 3 is single bonded. We're going to find that carbon number 3 doesn't really do anything. It's the double bonded carbons that get attacked.
So if you wrote propane on a test instead of propylene, that would be fine?
Oh, it would be fine, yeah. Yeah. I know how confusing that can get. Here you're trying to learn a system, and then I'm throwing other systems in there with it. Yeah, polypropylene is fine. So the initiator has a radical on it, that unpaired electron, attacks the double bond, and it bonds to the carbon on the left. So we have an R attached there. Now this carbon had its pi bond break, but there's nothing to attach to it. So it's got a radical now. There it is. Now this CH3, it had 8 electrons around it. It didn't do anything to anybody. And it doesn't get bothered or touched. So what has to happen is that CH3 is going to kind of rotate upward and get out of the way, because this carbon right here is angry. It's angry. See that? Angry. So what is going to happen now is, I'm just going to move this up. I have just taken that structure and brought it down here. It's the same exact thing. I just copied and pasted it down here. With the methyl group now up kind of on the top, this radical does what? It looks for a pi bond. And here's a pi bond. So it grabs it, attaches this thing to that carbon, then that carbon is now the angry one. And this thing grows. Now notice how it's growing. We have every other carbon has a methyl group coming off of it. It was that single bonded CH3, that one right there, is now a functional group on the parent chain. So that functional group gives that polymer different properties. And I'll just uncover this part too. The notation that we use, we have polymers. We use these parentheses with the lines. That would be the repeating unit. One repeating unit for polypropylene. You have to have both carbons in there because the carbons are not the same. Yeah, if I said show a repeating unit, you would do that. And that's normally what we do with polymers. I'm not going to ask you to draw 100 units of a polymer. That's silly. 1 or 2 or something like that. Or if I'm telling the truth. In the lab, I'm going to ask you to draw 3 repeating units of a polymer. But I'll never ask you to do more than 3. I promise.
And also, if you gave us like the thing on the lower right, would we have to name it?
No, you're not going to name any polymers.
Because they're too long.
But you may have to, given this, identify what the monomer was.
Okay,
Here's a polymer. What did you start with? For addition polymers, it's pretty easy because you know it had to start unsaturated. Just take that repeating pair of carbons and put a double bond on it. That's what you started with. Yeah, actually, the next thing that we do here, I'm going to take some of the Zumdahl problems in the book and show you, because the infamous number 72 in the problems, we get tons of questions about that one because of this. Undoing a polymer to know what you started with is not that easy. So we'll do that. I find this to be a very helpful guideline. if it's me taking notes, maybe you've already printed